In our last video, we started talking about simple harmonic motion. And in particular, we investigated the period of a simple spring block system. Remember that our starting point was to say, we'll use F equals ma to begin investigating what x of t looks like. This led us to setting up the differential equation, negative kx equals mx double prime, which we could then rewrite to isolate x double prime. And we got x double prime plus k over mx equals 0. And what we said is that this is now associated with an angular frequency omega squared and a solution x of t equals a cosine omega t plus phi. If this is all feeling unfamiliar, I encourage you to go back to the last video. And I state this here because we'll be relying on this result for today's problem, namely the simple pendulum. So the simple pendulum consists of a string of length L with a blob of mass m at its edge. We'll regard the blob of mass m as a point mass. And what we're going to do is displace our system by an angle theta. And our goal again is to determine the period of our pendulum. So what's our starting point? In the last video, we started from F equals ma. In this case, we're undergoing rotational motion. So a natural starting point would be to start from torque equals I alpha. So let's begin by thinking about the torque on this system. There are exactly two forces acting on our blob of mass m. There is tension inwards and mg down. And only mg exerts a torque about our pivot point. And I'll say that that torque is mg times L times sine theta, but in the negative direction. It is going against our displacement theta and pulling us back to equilibrium. And the first thing you might notice about this force is that it is not a linear restoring force. We'll return to that quite shortly. So at first glance, this does not look like simple harmonic motion. So next, we want to think about our moment of inertia. Well, we've got a point mass rotating a distance L away from our pivot point. So our moment of inertia will be ml squared. And so now putting all this together, we get negative mgl sine theta is equal to ml squared alpha. But of course, alpha can be rewritten as theta double prime, the second derivative of our angular position. Now at this point, I'd like to pattern match to the equation we had gotten in the case of the spring block system. So I'm going to go through the same process, rewriting this as ml squared theta double prime plus mgl sine theta equals 0. Of course, we can cancel out one factor of m. We can cancel out a factor of L. And lastly, we can divide by L, which leaves us with g over L, theta double prime plus g over L sine theta equals 0. And at this point, we need to think about whether this matches our prior differential equation. And unfortunately, it doesn't, right? X has been replaced with theta for the second derivative, x double prime, theta double prime, but then x itself has been replaced with sine theta. And so our conclusion is that the simple pendulum is not a simple harmonic system. So the good news is that in fact, we can rewrite this differential equation in some special cases. We're going to assume for a moment that theta is small. And let's go and jump and look at the graph of sine theta. For those of you who have already seen Taylor's series, you can feel free to skip this part. Go ahead and look at Desmos, and we plot sine of x versus x. What you'll notice is that the line y equals x follows pretty closely along with sine x. And in fact, if we zoom in, we can see that this holds extremely close to the graph of sine x, up to about 0.2 radians. And so why is this important? What we can now do is use the small angle approximation. So we'll state that for sufficiently small theta, sine theta is approximately equal to theta. And so now my differential equation becomes theta double prime plus g over L theta equals 0. And now we can fully pattern match to x double prime plus k over mx. The only thing that's changed is the variables, which have been replaced with theta, and the value, k over m, has been replaced with g over L. And so If here omega squared equals k over m, here omega squared will equal g over L. So what we now know is that omega equals square root g over L, and therefore the period of a pendulum is 2 pi square root L over g. In the next video, we'll look at applying exactly this approach to what we call a physical pendulum, namely one which might consist of a rod or any extended object which undergoes small oscillations.